Why is it relative? Why does water really?
There's a lot of stuff going on in that case. Okay, we're ready to go. And there's a lot of stuff going on in that case. Mostly, you are basically creating pathways that should not exist. You're creating electrical pathways that should not exist. So A should be connected to B, but A should not be connected to C. When you add water that conducts electricity with an electrolyte, A now connects to C, and C gets overcharged and breaks. Basically, C builds up too much charge and falls apart. Yeah.
What was the little red blinking light inside the camera when you charged the capacitor?
That was basically to tell the user that it's fully charged.
Oh.
It's a little tiny LED that's just saying, the capacitor is fully charged, you are ready to take your picture. So I'm charging it up, and when it's fully charged, a little orange light will start blinking. Say, you are fully charged. You know it's fully charged. And I can release that charge through the flash. I don't know why I'm looking at it. Or we can release that charge by short-circuiting the capacitor. So when I do use the flash, what I've done is I put a device in between. So the moment I bridge these two, the charger will be like, let's go back, and they go back. If I put something in between there, like a flash, I can harvest that charge and make it do something. Or I can just touch it with a conductor and short it out. That's what's going on there. Yeah?
So if you just had like, if you didn't take it apart and you were just like clicking the button and it was flashing, how does it charge? Like, does it automatically charge after each flash?
No, you have to hold the button down. You basically have to, it's so simple. Your camera automatically does that. Your camera keeps your flash, those LEDs, well, I guess nowadays we don't use those. We just use an LED that just turns on. But old cameras would have a capacitor that would constantly charge up and have like a little light, I'm ready to go. And that's what these do. You hold it down, and then a little light would turn on saying, I'm ready to go, and then you can press it. And it does take a little bit of time to get charged up. Like you saw, a little orange light. So if I was using this, I would hold down the charging button for, I don't know, 5 or 6 seconds, do the orange light, and I'll be okay, now I'm gonna take a picture, and you take a picture. Okay, so that's how it works. Okay, other questions? And again, to emphasize, the capacitor is charged by this 1.5 volt battery. That's it. Not a lot of charge being spit out at 1.5 volts because there's a lot of resistance in me, but you do not want to touch that. Well, maybe you do. It hurts. Okay, so there's the formulas, of course. There's a whole bunch of formulas for capacitance. In case you were wondering, the SI unit of capacitance is the farad, named after Michael Faraday. Pretty cool author, scientist, cool dude. And the amount of capacitance you can store is a function of the... You know what? I really don't like this formula. I prefer it to be this way. I like the amount of charge you can store is a function of capacitance and potential. I prefer to write it that way, Q equals CV. I think your green chart writes it C equals Q over V, though. Oh, your green chart writes it V equals C over, or Q over C, which is, that's dumb, yeah. I like to write it this way. The amount of charge you can store is a function of the capacitance and the potential. Now, 1 farad is an enormous amount of capacitance. In fact, a single farad capacitor is the size of a Coke can. Yeah, if you were to, with your left and right fingers, touch one pole of a fully charged 1 farad capacitor and the other pole for a fully charged capacitor, you're done. Yeah, there's enough charge traveling through you that even though you're a pretty good insulator, you're probably going to get yourself killed. So don't mess around with capacitors. This is a 100 microfarad capacitor. In other words, this is 1/1000th of a farad. It's a pretty good sized capacitor. These capacitors, on my 12-year-old video card, maybe 20 years old, it's a GeForce 7600 GT with 256 megabytes of RAM. Yeah, these guys are in the neighborhood of like 1.5 microfarads. This is what happens when they blow too. They heat up and they blow up. That's why I saved this. I'm like, oh, cool, glowing capacitors. Okay. Now, capacitance itself. We're almost done. Perfect for tomorrow's simulation. Capacitance itself is a function of the area of the plates and inversely proportional to their separation. So if you want a lot of capacitance, you want big capacitors, big plates that are really close together. So this is what you get when you unroll a capacitor. It's a piece of metal separated by a very thin piece of paper and another piece of metal. So paper, metal, paper. And then they roll it up. So you got a piece of metal, very thin piece of metal, then a very thin piece of paper, then another very thin piece of metal, and then they roll it all up. And the wider, the more area you have, the more capacitance you have. And the thinner your dielectric is, the more capacitance is. And then the E, epsilon naught, that is how good your capacitance is. This is the capacitance, or how good your dielectric is. This is the dielectric for air. Air's okay, it's okay dielectric. The reason this number is used is, this is the number that is used when we talk about charged things. In real life, there's lots, like cardboard is better dielectric. And then U is the amount of energy that is stored in the capacitor. So Q is the amount of charge that's stored, and U is the amount of energy that is stored in the capacitor. Okay, capacitors, let's charge. Okay, 1.5 volt battery, let's charge up. We are good to go. We have charged Q. Q is multiplied by the capacitance times the voltage. And then once it's charged up, we can discharge it by flash or zap. What's the capacitance on this thing? This guy has a capacitance of, I can't see because it's written on the other side. So this guy is this capacitor, this guy. This is a capacitance of, 100 microfarads. So this is, guys, this is a 100 microfarad capacitor being charged by a 1.5 volt battery. So if I ask you what the total charge you could store, it's very easy. It is 100 microfarads, or 100 times 10 to the negative 6 farads multiplied by 1.5. Alright, so we'll investigate this in a simulation tomorrow. If you didn't get your M&Ms, there's 3 little trays of M&Ms left.